It's time to make some of those ideas in the previous video formal here. Okay, so let's get going. If A is a square matrix and if B is a matrix of the same size, can be found such that A times B equals B times A equals the identity, then A is said to be invertible. If no such B can be found, then A is singular. Okay, so there is invertible and not invertible, and then singular or non-singular. I have heard all four of these words used, so this is quite ridiculous. If you just want to call them invertible and not invertible, that is totally reasonable, but you do actually see singular and non-singular a fair bit. Okay, so just FYI, those are the four things. Invertible and non-singular are the same, and singular and non-invertible are the same, and this is all stupid, so that's all right. All right, so next, it's not exactly clear whether or not there can be more than one, right? So right off the bat, if we had, 3 times what is 1, the answer is 1/3. Is it possible that there is another number? We don't know. Well, let's find out. Okay, so theorem 352 says if B and C are both inverses of the matrix A, then, oh, by the way, B is equal to C. Okay, so that matrix, that inverse matrix is unique. Okay, and the proof is actually kind of fun to do and something that you should think about because there's a lot of proofs that work this way in math. So I'm just going to kind of read through it here. Let A be a square matrix and let B and C be those inverses. Okay, so what you have is you have A times B and B times A is the identity, and you have A times C and C times A is the identity. So what we're going to do is we're going to compute BAC in two different ways. So in the first way, we're going to do BA and then C, and then the other way, we're going to do B and then AC. So we're going to do these in two different ways. And we know those are equal because of the associativity of multiplication. Well, BA is the identity, so BAC is IC, which is C. And A times C is the identity, so B times the identity is B. So when I compute it this way, it's C. When I compute it this way, it's B. And since those two things are equal, it means that B equals C. So we are done with the proof. And so we know that if there is an inverse, then it is there is only one matrix. And so we will shift to the notation that is A inverse. Okay, so note that same notation that we used in the real numbers of 3 to the negative 1, right? So like this is the same thing. And same thing with the inverse function. So again, we're not meaning to the negative 1 power here. This is a specific notation that means the inverse, okay? And once we understand what the inverse is, we still have some questions remaining. And those questions are, how can you tell if it's got an inverse? And then how do you find the inverse? All right, now I'll tell you there's a process, and we're going to start with the 2x2s. So we'll begin with the 2x2s because they're pretty nice. So what is it for 2x2s? If you have a matrix ABCD is invertible if and only if AD minus BC is not 0, in which case, here's the formula. So the inverse is 1 over AD minus BC, and you take these two and you switch them locations, so the AD and the D switch, and then you take the B and the C and you both make them negative, all right? So that's it. This thing on the bottom right here has a name, and we'll talk about that in the next section. So let's find the inverse. So if this is A, then A inverse is 1 over, okay, so it's going to be AD, so negative 2, minus 20 times, okay, now what we'll do, we'll switch those and then make those negative. And that's actually it. Now, I don't care really how we leave this. Negative 1 over 22 times negative 1. Actually, I think maybe a good idea. Negative 5, negative 4, 2. Maybe it might be a good idea to say 1 over positive 22 and then 1, 5, 4, negative 2. I don't know. However you want. They're all equal. Let's not worry too much about it. Do you need to sort of send this thing in? That's not necessary. That's not necessary all the time, okay? Like if you say like what is the inverse matrix, then of course it belongs in there, but just, over 22, over 22, over 22, over 22. So that's pretty straightforward. All right. Next, what about this matrix here? So if this is a matrix B, let's say, then what is B inverse? B inverse is 1 over, all right, 6 times 12 minus 8 times 9. and then 12, 6, and negative 9, negative 8. All right, 6 times 12 is 72, 8 times 9 is 72. Whoops. Okay, so this bottom thing just came out to 0. So what we know is that B is singular, right? Not invertible. And my kind of point in doing this is that's what happens when they're not invertible. And, you know, if you want to check that ahead of time, fine. Otherwise, generally speaking, what you do is you just sort of write down what the inverse is, and then you say, by the way, I had a problem. Okay, so the way you find out if it is invertible is you try and find the inverse, and then you run into a problem. Okay. Now, before we get to the n by n case, which we'll get to, I want to talk about how we're going to use these because this is very helpful for us. All right. So theorem 354 says, if A is an n by n invertible matrix and B is any n vector, then the system AX equals B, we talked about that being the matrix form of the system, has a unique solution, X equals A inverse B, all right? That is obtained by multiplying both sides of this line by A inverse, right? And that's very easy to look at. You just take AX equals B and you multiply both sides by A inverse, right? I started with A was invertible, so that's possible. Then I got IX over here, which is just X, and over here I have A inverse B, right? So it's that simple. So we can actually use this to solve systems. So this system looks like, if we let X be the vector X, Y, then A is the matrix 3, 2, 5, 3, and B is the column 5, 1. Okay. Well, what's A inverse? So A inverse is going to be 1 over 9 minus 10. Wait, did I already do that one? 3, 2, 5, 3. Nope, I didn't. Okay, well, that's all right, we'll do it. 1 over 9 minus 10 times, okay, we switch the 3's and we make these negative, negative 5, negative 2. We see that that's negative 1, so this is just negative 3, positive 2, 5, negative 3. So there's the inverse. And so I can solve this system by simply saying that X is going to be negative 3, 2, 5, negative 3 times 5, 1. And then just do the calculation. So negative 3 times 5 is negative 15 plus 2. Negative 15 plus 2 is negative 13. 5 times 5 is 25 minus 3 is 22, and I'm done. There is the solution. So X equals negative 13 and Y equals 22. Is that particularly efficient? Well, I don't know, maybe not. But there is a time and a place to need something like this. Okay? Couple last cleanup theorems here before we get to the n by n case, and it's this. So if A and B are two invertible matrices of the same size, here's what we've got. The inverse is invertible, and the inverse of the inverse is the original. Okay, so of course it is. That makes sense. All right, what matrix do you multiply A by to get the identity, right? And the answer was A. So A is the inverse of the inverse, and of course it is. If n is a non-negative integer, okay, so integers are the whole numbers that are positive and negative, only the positive ones are the whole numbers, then a to the n is invertible, and the inverse of the nth power of a is the nth power of the inverse. And that actually also makes sense too, because if you have a multiplied with itself a bunch of times, can you multiply that with something to get the identity? And the answer is, sure, just a bunch of the A inverses, right? So as you multiply these, they slowly identity sort of, collapses from the inside. Good. The last one is the product A times B is invertible, right? If they start off with invertible, then if you multiply them, you're still invertible, and the inverse is B inverse A inverse. Now, the cool part about this is that all you have to do is verify that it works, okay? So what we're going to do is we're just going to verify. So what do you get? AB times B inverse A inverse. Well, that is A times B inverse A, which is AIA, which is AA inverse, which is I. So what we just discovered is that this thing is the inverse of this matrix. And so that means that the inverse of this is, in fact, B inverse A inverse because it is unique. That's worth thinking about a bit, okay? Because this thing in the parentheses is the inverse of this thing in the parentheses. And so this thing in the parentheses is the inverse of this thing in the parentheses. So there we go. I think I just said that the same way both ways, but you know what I meant. Okay, in the next video, we will talk about how to find the inverse of bigger matrices, and there's a process, and it's not so bad. So I will see.